Hello students, welcome back. Lesson 7 is a continuation of Lesson 6. So let's begin with a review. It's going to be a very brief review. A random variable is a real function that assigns a numerical value to each outcome of the sample space. We already discussed it many times already. If it takes only a discrete set of values, then we say the random variable is discrete, and in which case we can define the probability mass function like this. And then from here, we can define the expected value, variance, standard deviation, and all kind of things, including the CDF, the cumulative distribution function. Interestingly, from CDF, we can go backward and define probability mass function by inverse operation. From PMF to CDF, we take accumulation, that is, repeated addition of probabilities. If we go backward, we can go from CDF to PMF through repeated subtraction. And that is important because this mass function is not always valid. If your random variable is not discrete, then this concept is no longer useful. But the concept of CDF stays valid, and that's where we're going to start. Let's consider a special case when your image set of the random variable is an interval. Interval, say 0 to 1 or 0 to infinity or negative infinity to infinity, those kind of things. And then let's consider a special case where the cumulative distribution function, defined the same way, is a continuous real function. In that case, we say the random variable is continuous. So the continuity of the random variable means the continuity of the CDF. Here are a couple of visual examples. Here we go. Here are a couple of examples of CDFs. We begin from 0 as usual, when nothing was accumulated. Now add up the probabilities infinitesimally. Eventually everything was added, so end up at 1. Same here, start from 0, increase, and end at 1. That's how the CDF works. Now previously for discrete random variables, we added a chunk and then another chunk and another chunk of masses like those, so we had jumps. But this time, no. This is continuous because we are adding up infinitesimally. And all those probabilities are non-negative, so CDF never comes down, always increasing and continuous. Now for those, it is possible to define something called a probability density function with this property as an integrand. And furthermore, if your capital F, the CDF, is differentiable, then the probability density function is the derivative function. Why? It comes from the fundamental theorem of calculus. Look at this. Integral is equal to the net change, isn't it? It comes from the fundamental theorem of calculus. But this is always 0 because nothing is accumulated yet. So throw away the 0 part, and here we go. So this comes from the fundamental theorem of calculus. If the probability density function is continuous and capital F, the cumulative distribution function, is differentiable. Interestingly, this holds not only when capital F is differentiable, but even if it's just continuously increasing as well. But that's a bit too deep, so let's stick to a simpler case where capital F is differentiable and small f is continuous, in which case we get this kind of visual examples. First row, we have the visual examples of probability density functions, and then the probability in the interval corresponds to the integral from a to b. And by the fundamental theorem, the integral is the net change. And that's how they are related. So the probability is the area if you look at the density function. and it's a net change if you look at the cumulative distribution function. So for density function, we have area. For distribution function, we have the net change. Why? The fundamental theorem. There are some further visualizations too. Many times, the probability density functions appear as a limiting cases for discrete random variables through probability histogram like this. Like this. So histogram versus the density function as a limiting case. And if you do the same thing to CDFs, we have OGIFs. So we have these step functions, but more and more and more class intervals. And what do we have? We have a CDF. See, so for CDF, OGIF. For PDF, histogram. By the way, this kind of limits do not always take place, but many times they do. And in this level, at 3000 level, we're going to stick to the examples that they do. Especially, we're going to focus upon this case here, the normal random variable. And that's going to be the topic for the next section here, section 2, which will start in a separate video. Stay tuned.